Okay, so good morning to all, and welcome to this lecture on AMD GPU programming with HIP. We're on day 5 of this 6-day course now. We have completed so far. We've completed the introduction to HIP and basics of HIP computation and memory. We completed HIP memory yesterday, and as a small recap of what we've seen so far, we got introduced in the first lecture. We saw what the AMD hardware is and what GPU programming is and what it's used for. And we saw that the hardware is split into compute units and further into work groups and wavefronts. Then we saw HIP computation where we started programming in HIP, and we saw simple programs, and then we saw how to use threads, how to launch kernels, and the requirement of a barrier between host and device. Then we moved on to HIP memory, where we saw the memory hierarchy that is used in AMD GPUs. We saw that we have a global memory, then we have L2, L1 caches, and then we have memory units which are local to a thread, which are registers and private local memory. And we saw how to use the local data store to get an improved performance. And then we saw how to use structure of arrays and array structures and how memory coalescing works and how it can be beneficial to us. Does anybody have any doubts in any of the topics that you've seen so far? Okay, so we'll move on to another interesting topic when it comes to GPU programming, which is synchronization. This is a pretty important topic that we have to learn when it comes to concurrent programming or in any place where we have multiple uh, workers trying to manipulate the same data location. So this is very important when it comes to GPU programming or wherever we have multiple threads. So we'll start with the basics of synchronization. So the question is, why do we need synchronization? So as I said, we need the data to be consistent, which is that all the writes and all the reads made by multiple threads should be visible to everybody else, or it should be that the data that a thread reads is consistent with what all the other threads have written or are seeing. And we need synchronization to keep an ordering between instructions across multiple threads. I think in the computation section, we saw an example where we printed the thread IDs from 1 to 1000. We saw that there's a problem when it comes to printing it, and it goes out of order. We don't get the expected output. I mean, we did get the expected output, but if we want to add an order, like if we want to print it in increasing or decreasing order, we need some sort of a synchronization to make sure that it gets printed in the right order. And then we need to avoid race conditions. And also, synchronization can be pretty helpful when it comes to maximizing the concurrency. So we start with what is a data race. So a data race occurs when multiple threads, two or more threads, access the same memory location at the same time, and at least one of those threads try to write to that memory location. So this is a problem because like if one thread writes to it and another thread also writes to the same location, it is possible that one of these writes may not be visible. So when can a data race occur? A data race can occur if these four conditions hold, which is that more than one thread is involved and they all access or they all try access a common memory location, and at least one of them is a write. It doesn't have to be multiple writes. If at least one of them is a write, then we can run into a problem. And all these threads are executing concurrently. Now, if we can remove at least one of the above conditions, then the database can be avoided. So, how can we do that? One is that we can execute the code sequentially. But there's no point in executing it sequentially because obviously we're trying to do parallel programming. So we want it to be as parallel as possible, as concurrent as possible. Or another way is that we can duplicate the data, which is that keep different copies of the same data. Another way is to separate the reads and writes with a barrier. So we'll see what a barrier is towards the end of this lecture. And finally, we have mutual exclusion, which also we'll see in detail today. Now, we'll see how a data race occurs. So we can see that this is a very simple kernel. Let's assume it's launched with 128 threads and a single block. This kernel is pretty straightforward. It just creates a variable TID, which is the thread ID, and then if the thread ID is 0, then it increments the value at location A of 0, value at location A with the value 10, and if the thread ID is 64, then it updates it to 20. And we assume that A of 0 is initialized to 0. Now, here a data race is we can get a data race. That is, we can get there are multiple possible outputs that we can expect here. So how does that occur? We'll see. So the multiple different outputs that are possible are we can either see a 10, we can see a 20, or the expected values that we should see a 30. So any of these three values are possible here. So this is a breakdown of what exactly occurs when we what exactly is occurring like at a hardware level or at an instruction level when we execute let's say AF0 plus equal to 10. There's a typo there. So if you take thread 0 and if you're taking the statement A of 0 plus equal to 10, that instruction can be we can further break down that instruction into three uh, basic instructions, which is that first we load the value at A into a register R1, and then inside that register R1 we are incrementing the value by 10, and then we are storing the value in register R1 into the memory location A. So this is how we can break it down into even further instructions. The same is applicable to the thread 64, which is updating the value to 20. There's a typo at that line number. It should be TID equal to 64. There also the same operations are done when we update it by 20. It's that you load value of A into the register R2, whatever is the existing value of A into R2, and then we update the value at R2. R2 is a register, R2 with 20, and then we store the value of R2 into A. So yeah, the thing is that both thread 0 and thread 64 we can execute in parallel. Like at the same time, AF0 plus equal to 10 is happening. AF0 plus equal to 20 can be executed by thread 64. So that is where it happens. So the condition that all the threads should be executing concurrently is held, and the fact that they are writing to the same memory location is also true. And of course, one of them is a write. So all the conditions we can see are satisfied here. So it's possible that a data race can occur. So we'll see how exactly it is possible. So consider the following sequence of operations that this is how these operations in time. Let's say thread 0 executes its first instruction, which is that it loads the value of A into R1. And the initial value of A is 0. And then thread 64 also executes its first instruction. So that also loads the value of A into register R2. So both A and B, both thread 0 and thread 64, they would have loaded the value of A, which is 0 into R1 and R2. Now thread 64, let's say it updates the value of its register by 20. So right now R2 contains the value 20 because R2 initially contains 0, which was held by A. And then T0 executes its second statement, which is that it increments the value of R1 by 10. So this means that R1 will now contain the value 10. So R2 contains 20 and R1 contained 10. Is Milan, you've raised your hand. Do you have a question?
So Matthew, a quick question here. So I assume the individual threads will execute the instructions in serial. So it's either thread 64 or thread 61 that executes all the instruction at once.
You're saying within a thread are these instructions serial?
Yes.
That is true. So first the load will happen, then the update will happen to the register, and then only the store will happen.
So the interleaving that we see on the slide shouldn't be there.
No, so if you see the ordering across it, it's like T0 first happens, then the second statement, and then the third statement, right? Like there's no out of ordering happening here.
Okay. So my understanding was that probably T0 1 2 3 would happen, and then T64 1 2 3.
No,
Or
no, no. Okay, so T0 1 2 3 would be executed serially, but these instructions can interleave, right? It's possible that they can happen at different times at the same. I mean, they can get interleaved. Why would they not get interleaved?
because the CPU or the program counter will point at one. So if the context switch happens between these two threads,
Huh.
so the program counter would uh, go from one instruction to the other in a page. So my opinion was that it's either 60. The interleaving is between either 64 gets executed first, or on the
You mean
zero thread.
all of?
Yeah.
But how? Like, is it not possible that if the context switch happens, then after the first instruction happens, then the first instruction of 64 can execute if a
Yeah.
context
That
switch happens?
okay. Yeah. That also okay. Yeah. Now I get that. Okay. So context switch will happen between.
That's
Okay.
a possibility, right? Like if you're talking about if it was thread 63 in this case, then that would not happen because they'd all be executing in a single uh,
Okay. Okay.
indeed.
So this is classical operating system.
We can
Right.
look at it from that perspective as to explain this data race.
Right. Okay. Thanks.
Yeah. Okay. So here we see T64, which now, as I was saying, so R2 will contain the value 20, and then R1 will contain the value 10. And as then thread 0 executes its third statement, so it stores the value R1 into A. Now, which means that R1 will contain the value, A will contain the value 10, and then 64 will update the value of R2 into A, which makes A as 20. So what happened here is that the update made by thread 0 is lost. So the value of 10, it was overwritten by the thread 64 because it executed its store at the end. So yeah, how can we overcome this data race? So we can make sure that the expected value was 30, but we got some other value, and the situation where the final value depends on the sequence of instructions or timing. This is called a data race. So what we need to do is we need to make sure that this load, update, and store happens atomically. Only then um, we can make sure that the value is consistent across different runs. Or yeah. So we'll see some frequently used terms here, which is that deadlock and what starvation. So deadlock is a situation where like multiple threads, two or more threads are just stuck at a point because uh, they're waiting for each other to release resources. So let's say thread A wants a specific resource and thread B wants another resource. Let's say two resources, and A is holding one resource, B is holding one resource, and B wants the resource held by A, and A wants the resource held by B. So that is a situation called as a deadlock because nobody's moving forward. Everybody is just waiting for each other to release their resources. So this is from explaining from a classical operating systems deadlock perspective. And then we have what is called as a starvation. That is when starvation is it's not as serious of an issue as a deadlock, but it occurs when a thread is it's not treated fairly. That is like if we have multiple threads trying to let's say execute a piece of code, and let's say thread 0 and thread 1 is there, and thread 0 comes and waits for thread 1 to complete its execution. And as soon as thread 1 completes its execution, thread 1 again comes to execute the same piece of code. So this would lead to a situation where thread 0 is eventually waiting, but there's nothing stopping it from executing. The only thing is that the scheduling is happening in such a way that it's uh, unlucky for thread 0. So, what are atomic operations? Atomic operations are just a set of operations which runs independently of any other operations, and it is uninterruptible. So, these set of instructions they'll execute as a proper sequence. We can't interleave them with any other operations. So, this is very important when it comes to data consistency, and we need some ordering between threads. So in our previous example, we want all the three sub instructions, which is load, update, and store, of a single instruction to happen atomically. But it is possible that they will get interleaved. Yeah. So we want them to execute atomically. So here's a small question as to where atomics can come into picture, or we need to see if it comes to picture. So given the marks of all students in a class, we want to calculate the number of students with a specific grade. So let's say we have A, B, C, D as the grades, or A, B, C, D all the way up to J as the grade. And students with marks greater than 90 will get an A. Between 80 and 90 will get a B, and so on. So we want to calculate, we are given an array of all the marks of all the students, and we want to calculate uh, how many students from each grade exists. So, and we want to store it in an array. So how is it possible? You can take a moment and think about it, and you can think if we need atomics here. We can think of it from a perspective. We can take it as a GPU problem itself, where we have multiple. Let's say we launch a thread for each student in the class. So, do we require an atomic operation here? And if so, where will we be needing it? You can take 1 or 2 minutes and just put your idea in the chat box. Balancing the common array where the count of grade is being stored. Okay. So the entire array or each element of the array, Milind? Viren is saying we don't need atomics because there are no common write locations. Okay, so let's say we have a grade A, grade B, grade C, and so on. So for each of these grades, we'll be having a memory location in one of the in the array, in the output array. So output array of 0 will indicate how many grades and how many grade A students are there in the class. So A Learn is saying int A is a 4 enum grade equal to 0.
Precisely what you were saying, as in let's have an array of size 4, and the 0th index is the number of students having grade A. The first index is number of students having grade
Yes,
B.
correct. Yes. So would we require an atomic for like I didn't get your first statement as to the common array where the count of. So you're saying we need atomics for the.
Correct. We need the whole access to the array should be in the critical section. Again, the OS terminology if you're using.
Okay. But can we make it a little more fine grained, because if you're locking the whole array, that can lead to. I mean,
because
it works.
we don't know which student has been given to which thread. As in, I can sort the array and group it, but yeah, again, it will defeat the purpose of parallelism.
Okay.
So
Okay, so we'll see how we do it in this case. So Viren is saying we don't need atomics, but wherein we are like writing to the same location, right? So the output array will contain one of these locations will indicate how many students are there from that specific thread of specific grade. So we will be updating one common location. So we will need atomics here. And Pranod is saying in case of multi-thread operation, atomic operation will be, yeah, that's correct, Pranod. We will be needing atomics because there are multiple threads. Yeah, okay. Okay, well, that is. So I'm hoping the question is clear to everybody. So we're given a big array. Let's say there are 100 students, and we're given the marks of all the students in this array, and we want to calculate the number of students with a specific grade. So let's assume we have grades from A to J, and we want to find out how many students have a specific grade A, how many students have a specific grade B. So our output array will be a array of size 10, where A of 0 indicates how much is the number of students with grade A, and A of output array of the second element will indicate how many students are there with grade B, and so on. Yeah, so that is the question. So in a serial sense, we'll be iterating over the array, and we'll check what the mark of the first student is. And if it is in this range, then we'll update the resultant array at that specific index. So if the first student has a grade 95, then we'll do resultant array of the output array of 0th index, we'll increment it by 1, and so on. So that's how we'll do it. Now, how do we do it parallelly? And we'll see this question in detail. But so the idea is that instead of locking the whole array for all the operations, it's only that we just need to update. We just need to have atomics on each element of the array rather than the whole array itself. So if we put the whole array in the critical section, so what happens is it becomes kind of like it's a totally sequential operation. So rather than that, if let's say we launch 100 threads for, we launch a thread for each of the students, and each student will each thread will see what is the mark of that student, and depending on the range in which his mark is there. So like if his marks is in the grade of 80 to 90, we'll give him B grade, and then we'll update the array, which will be the output array of the second index of the output array. So multiple threads are writing to the same location, but it's that based on the grade, these locations will be different. So rather than locking the whole array and then updating the specific index, we can lock only the specific index, specific array index, that location, and then we can proceed. So that would give rise to a little bit more parallelism than locking the whole array. So is the idea clear to everybody? If you have any doubts in I think I should have added the code, but I think I missed that. Okay, so this is a idea which was given by Millen, which is that only one write happens to the entire array. That is, so we'll see what locks are in the in as we move along. In a wavefront, what if one thread is blocking and the others are not? Uh, one thread is blocking. If you're talking from a logs perspective, then yeah, that will be a problem, and we'll see that example today as we move along. Yeah, Viren. But at this moment, for this question, we don't actually need logs. We just need to atomically increment a specific location rather than locking the whole array or even locking the specific memory location. As in, the idea of critical section does not come into picture that much here. But we just need the increments which happen to a specific location, which is to a specific grade, to be atomic. That's all that we need. Okay. So this is a piece of code to do SSSP, which is the single source shortest path algorithm in parallel. So there are a few constructs here which are not like from the standard implementation, which is that we have an object of graph, which essentially, and I've added some pseudocode here so that it's easier to write the code. So what it does is it checks the neighbor. We're launching this kernel for each node of the graph, and what we're doing is we are iterating through all the neighbors of a specific node, and then we're calculating the distance from the current node to the neighbor node, and we check if this new distance, if it's less than the existing distance to the neighbor, then we are updating the distance to the neighbor with the new distance. So it's the standard SSP algorithm. It's just that it's running in parallel. So in this implementation, where do you think something can go wrong? You can take a moment and then come up with any answer if you have any, or can this work properly? Obviously, because we are dealing with atomics, there will definitely be some problems, but can you identify where that problem might be? Yeah, Milton, you're right. So that is where we'll have a problem. We'll need atomics to assign it to that, assign this new value to a new distance if it is less than. Yeah. So we'll see the actual solution as we move along. Now we come to mutual exclusion. So what is mutual exclusion? So mutual exclusion is just it's a concurrency control property that ensures that like multiple threads or multiple processes do not simultaneously execute like some set of instructions or some sequence of instructions which probably has let's say some memory location or some shared resource. Yeah. So these sequence of instructions which access a shared resource or a shared memory location is called, what is called as a critical section. So we only want one thread, or depending on our needs, we may need more than one thread. But let's just for the time being take that we only need one thread to execute the critical section at a specific instance of time. So it is crucial for we need if you need data consistency and to prevent data races, it is crucial that we have mutual exclusion. So some mutual exclusion constructs which are quite popular as locks, semaphores, and monitors. We use them, I think, frequently when it comes to operating systems. Anybody has any doubts in the basics of synchronization so far we've seen with atomics? This question. Saurabh, I hope your doubt was cleared about locking the whole array. Okay, okay. So what exactly locking means is that, so I just spoke about critical section, right? So locking would mean that we put the whole array in the critical section. So uh, all threads will try to access the array, but only one of them will be allowed to access the entire array. Which means that none of the elements in the array can be updated. Only one of the elements in the array will be updated by one of the threads. Okay, I think I'll explain it once I've completed logs. So at that point, it might be a little more clearer. Okay. So how do we implement mutual exclusion? So this is a simple mutual exclusion construct. Is there a problem with this implementation? So what happens is we just assume that there are two threads, and one thread will execute this construct, and this other thread will execute this piece of code. And S1 and S2 essentially indicates some statement uh, which contains maybe a common memory location or something. So can this will this work? And we have made some assumptions, which is that writing and reading a flag is atomic, and both the threads are executing concurrently. And flag is a volatile variable. So I'll explain what volatile is. Can this work? So the thing is that if you take two threads and both of them, and let's say flag has some initial value which we don't know. So both of them will try to execute their own piece of code. So let's say T0 executes the um, code on the left side and T1 executes on the right side. So so flag will initially have some value. Flag is a Boolean variable, and it might have true or false initially. So if the value is true, then the while loop of thread 0 will become false if the flag initial value is 0 and flag initial value is true. In that case, the while loop will break, and thread 0 can execute S1 because the initial value of thread 1 is thread 0 is sorry, the initial value of flag is true. The while loop of the second construct, which is on the right side, that will be stuck. So it will be while true, and it will just keep busy waiting on that loop. So this essentially does ensure that it's mutually exclusive, provided that we take these assumptions into picture. So what is a volatile variable? So volatile variable is a variable which is reloaded from the memory every time it accesses the variable. So some thread accesses the variable, and if that variable is volatile, then we fetch it from the memory rather than using using some value which we may have stored in the inner register or in the cache. Not sure what cache is, but definitely in the register, if we have a value, we'll not be using that value, but we'll fetch it from the memory every time we want to access that variable. So, and every write will also be committed directly to the memory rather than being kept in a register. So, but we shouldn't use volatile variables a lot because it is actually problematic when it comes to optimizations. So, if we can't keep variables in the register, which means that things will be a lot slower if we are writing it to the memory every time. So only when we absolutely require it, we should use volatile variables. So now we'll, with whatever little understanding we have of mutual exclusion, we'll try to implement lock and unlock functions, which is that these functions will be placed before and after the critical section. So as I said, critical section is a set of instructions which will definitely which try to access a common memory location. Essentially, critical section will contain some piece of code which we want only one thread to execute at a time. So lock and unlock essentially will make sure that only one lock will make sure that only one thread will come into the critical section. So lock will be placed before the critical section, and lock will be placed after the critical section. And these should be general functions which we can use for both threads. But like if you saw in this example, we can see that these are different. We can't use because the locking mechanism used for thread 0 is while not flag, and for thread 1 it was while flag. So we should have a common implementation which can be used for both the threads. And we'll assume that the thread IDs are just 0 and 1. So you guys can take a moment and then come up with some ideas. You don't have to write the code. Just you can, if you have any ideas of how to implement this lock and unlock, we can just put it in the chat box. Shared Boolean lock. written using a lock variable which is shared. Um, how will it help with locking? But we only have two threads, so we'll assume that it's from the same block. Okay, so this is one solution which we have, and of course we're not using the GPU constructs here. We're just showing how to do mutual exclusion from in a general sense. So we'll keep a Boolean array, which contains two booleans, which is we'll name it as flag, and so flag of 0 will be used for thread 0, and flag of 1 will be used for thread 1. And this is the idea of a simple lock. So this lock function will be put before the critical section, and unlock will be put after the critical section. So what we do is we'll create two variables, my ID and other ID. Which so my ID will contain the thread ID of the current thread which executes the lock, and the other ID will contain obviously one minus that. So it'll be either one. My ID will contain one. In that case, other ID will be 0. And if my ID contains 0, the other ID will be 1. And flag of my ID will be updated to true. So which essentially means that like if that statement is executed, it means that the current thread, or I am interested in going into the critical section. So if the flag of 0 is true, that means that the 0 thread wants to go into the critical section. And then what we do is we wait. We'll check what if the other thread also wants to go into the critical section, and if the other thread wants to go into the critical section, then we'll wait here. So if flag of other ID is true, then while true will while true will happen, which essentially means that it will just busy wait on that while loop. Busy waiting means that it'll just keep on executing the while loop without doing any useful work. So the thing is that this essentially ensures that mutual exclusion is there, but there's a bigger problem here when we execute this piece of code. Can anybody just think about what can go wrong with this implementation? Like so, both threads, thread 0 and thread 1 can try to execute the log function at the same time, and the instructions can be interleaved. So what is possibly going wrong here, or what can possibly go wrong with this implementation? Prasanna is saying this is similar to a traditional mutex with a higher number of threads. Yeah, that is true, because there will be a lot of threads busy waiting, and it will be inefficient. But this kind of implementation will not only be useful for two threads. We can't have more number of threads. If that's the case, then because our implementation itself is kind of like that, right? So we're using my ID is equal to thread ID, and then the other ID is 1 minus my ID. So that would essentially mean that we can only have two threads. But what you're saying is right. When we have busy waiting, and when we have a lot of threads doing busy waiting, that is essentially making our whole system inefficient. So the bigger problem here is that this kind of an implementation can easily lead to a deadlock. So okay, one thing I have to mention is that primitive type. Okay, before that, I'll show you. Let me just check. So how can a deadlock occur here? So let's just yeah, that is true. A variant has said that it can lead to deadlock. Yeah. That's correct, Viren. So, how does it exactly lead to deadlock? So, suppose both thread 0 and thread 1 try to run the lock function. So, first, both of them will calculate my ID. So, my ID is a local variable to each of these threads, and the other ID is also calculated. Then, suppose the third instruction, which is flag of my ID, is executed. At that point, both thread 0 and thread 1, they might set flag of my ID to true, which is that flag of 0, and flag of 1 will be set to true. And then when both of them execute the next instruction, which is while flag of other ID, both of them will just get stuck at that line. So both of them will busy wait, and they are just waiting for the other one's flag to get to false. But that will never happen in this case. So both of them will just eventually wait. But in a case where yeah, Pranod is saying flag of other ID. Yeah, that is true, Pranod. There is a specific set of ordering of instructions or a scheduling where if you're unlucky, the timing can lead to both the threads waiting for each other to get over. So essentially, that is a deadlock situation. But it is also possible that, but mutual exclusion is guaranteed in either way. But if it leads to deadlock, then yeah, we have a bigger problem. Suppose if they don't execute a flag of my ID equals to true at the same time, then we'll definitely get mutual exclusion. So there's one important thing that we have to note here is that primitive type assignments. So say integer or float or char. These kinds of type assignments, that is a write to a primitive assignment, will be completed in a single machine instruction. So we can be definitely sure that they'll be atomic in nature. Like if two threads are writing to a specific memory location and that happens to be an integer, then that update, only one of these updates will be visible, but we can't say which update will be visible. Say if thread 0 and thread 1 is trying to update int of a, and thread 0 is updating to say 10 and thread 2 is updating to 20, we can definitely be sure that only one of these updates will be visible. It's not like a mixture of these updates will be seen as a output. So it can either be 10 or 20. It won't be some other, let's say, unexpected value in this case, because the assignments are usually in a single operation, and at least that's something that the hardware guarantees, that the primitive type assignments are atomic in nature. So yeah, they'll not be. We won't have the same problem which we saw when we did a plus equal to 10. That kind of issue will not be possible in this case. So in the previous example, as I said, mutual exclusion is guaranteed, and deadlock is possible. Like I said, when both of them update their flags to true, and both of them wait in the next while loop. Now the question is starvation a possibility here, which is that thread 0 or thread 1 just keeps on executing, and it never gives opportunity to the other thread to execute. Is that a possibility here? So the fact is that it is true that it can keep on executing the same critical section again and again. In one of the, like suppose thread 1 executes the critical section while thread 2 is waiting, and thread 2 makes thread 1 unlocks, makes the value as false, but immediately comes to the lock function again. Before the thread 2 can get scheduled, it makes its ID as true, and when the other thread tries to, well, they may diverge when threads within the same group. Prasanna, where exactly is the divergence happening? You're saying within the while loop, is it?
Yeah, when you have threads within the thread block.
Like you're talking about the while loop, that's where the
yes,
that is possible. Yes, correct.
If I mean, not all scenarios. Again, if threads require mutual exclusion, some threads require mutual exclusion, while there are some threads which don't.
Yeah,
Then
that
they
is
may
correct.
diverge.
Threads will diverge when it comes to multiple threads within. But when you talk about well,
Will keep.
divergence comes into picture when we talk about wavefronts.
Okay.
Threads within a wavefront. So when it comes to dealing with wavefronts, we have a different problem which we'll see as we move along. Which is that threads may hang. Like I think Viren had mentioned earlier regarding this, but so it is possible that the threads may hang. So we have to handle it a little differently. But yeah, divergence will happen because certain threads will be certain, like one thread will be executing critical section while the others will be doing knob. So yeah, divergence will happen.
Okay. So okay.
Yeah. So once we reach that section, we'll see again how exactly this happens and how we'll deal with it.
Okay.
So, can we prevent a deadlock in the previous solution which we just saw? So, this is another implementation where we use a single variable rather than an array of booleans, and this is a volatile variable. So, what it does is if it just makes myself, like if I'm the current thread, I'll just make myself the victim, and if I'm the victim, then I'll just receive it. And yeah, so that's the whole idea. So in this case we won't definitely get a deadlock, and mutual exclusion is also guaranteed. But again here starvation is something that is possible. So you can have a look at this code and then see if you have any doubts regarding how deadlock can be prevented, or if there is a case where deadlock can happen. So the victim variable will be updated. So the victim variable will only have one value at a time because it's a volatile variable, and in either way, it's just a primitive type assignment. So either of the thread IDs will be updated. So either it will be 0 or it will be 1, which means that the while loop will definitely break in one of the cases, in for one of the threads. So yeah, starvation is possible though because the same thread can keep on executing the lock code, and the other thread may just will not proceed. It'll just be in that while loop. But starvation is not something that can be guaranteed because it's possible. It depends on how the threads get scheduled. So yeah, but we can obviously overcome starvation with some different constructs, which we'll see in the next slide, which is that we'll be using something called as a Peterson's lock, which the victim will be equal to my ID for both. So thing is that my ID, the value of my ID will be different for both threads because my ID is thread ID x.x, right? So for thread 0, my ID will be 0, and for thread 1, my ID will be 1 because the my ID is a local variable to both the threads. Is okay. Okay, so for now we'll take a break for 10 minutes and then we'll come to Peterson's lock after the break. So does anybody have any doubts regarding what we've seen so far?
Well, just a quick question.
Yeah.
So if we are so when you're implementing atomic, right? Are you calling any specific primitive, or it's just standard atomic that will take care of atomic operations on target device?
Sorry.
For atomic operations in previous slides.
Okay. So we'll see atomic operations. So we've not seen any atomic functions so far. Like there are built-in functions which are provided by the HIP runtime, which takes care of atomic updates. And we'll see an example of how to use atomics to implement locks as well. So far, what we've seen is just not specifically related to GPU. We are trying to do it from a CPU perspective so that we can understand these concepts.
Got it.
But yeah,
Okay.
atomics have to be supported by the hardware. Like there is nothing at the software that we can do to make sure that atomics is implement. Like we can implement at least one of the atomic operations. So there is a atomic instruction called as atomic compare and swap. So if we have at least this at least this function, then we can definitely uh, implement the other atomic functions. So we'll see that in the further slides.
Okay, got it. Yeah, and also, how are you analyzing all this? Do you do static code analysis, or do you have uh, even if you have to detect any bottleneck or deadlock on GPU? Do you have any profilers specific to that, or how are
We
you?
have profilers for CUDA. I've not used profilers for HIP, but as to how exactly deadlocks is possible, I've not tried doing that using a profiler. But that's just if you order the instructions and if you can get a scenario where it's possible, then yeah, like I've not actually used profilers to check for deadlocks.
Okay.
Yeah. Okay, so if there are no more doubts, we'll take a 10-minute break till 10:35 and we'll resume with Peterson's law.
Thank you.
Yeah. Okay, so we'll see what Peterson's lock is and how it prevents mutual exclusion, deadlock, and starvation. So Peterson's lock essentially uses both the ideas from what we saw in the previous two solutions, which is that we use a Boolean array of flags. I mean, a flag which is a Boolean array, and then a victim variable. So essentially, the idea is simple. We have the my ID and other ID variables, and then if I'm interested, if the current thread is interested in going into the critical section, it sets its flag as 0, flag is true, and then it makes itself the victim again. It assigns the victim variable as its own ID, and then it checks if the other variable, if the other thread wants to enter the critical section, and if I'm the victim. So if the other thread does not want to go into the critical section, flag of other will be false. In that case, this while loop will break. But if the other thread wants to go into the critical section, and if the current thread is the victim, in that case, it will wait. So if the current thread is the victim, it means that it essentially means that the other threads would have already gotten into the critical section. So this idea is to combine both the previous solutions so that we get a combination of mutual exclusion, deadlock free, and then starvation free solution. So you guys can just take a minute and look at this solution and see if you understand it properly. If you have any doubts, you can ask now. It's a pretty important concept when it comes to not just GPUs, but in the whole idea of operating systems or concurrency for that matter. Okay, so in this case, is it Saurabh? So suppose so starvation happens, like I said, when there are multiple threads and they're not treated equally in a sense. So if the first thread, if thread 0 executes the critical section and then unlocks the and then executes unlock, and it goes again and then acquires the lock and then enters the critical section and so on. So this case leads to starvation. So if there is a thread 1, then that thread will not be scheduled. It will not be able to enter into the critical section. So when is this possible? So here, if you see that, let's say thread 0 and thread 1 exist, so both of them execute this first statement. So my ID will be 0 and 1. And either one of them, so let's say victim equal to my ID, will be executed by both of them, let's say. And it just so happens that, and we are assuming that both of them are executing this sequence by, line by line. But it just so happens that victim equal to my ID, that execution happens first for thread ID 1. So victim equal to 1 will always be true for the second thread. So at that point, the thread 0 will break its loop and then go on. And meanwhile, if the if thread 1 is preempted and thread 0 executes the critical section, doesn't unlock, so victim equal to victim becomes 0 at that case. But since thread 1 is preempted and not in execution, it can come again and then execute int my ID equal to this thread ID x.x, and then it can make victim as 0. Actually, in this case, it will not be possible. I think if the assignment to victim equals my ID, if it's waiting in this loop, then in that case, starvation will not happen. If thread 1 is waiting in this loop, in that case, whenever it gets scheduled, that will break out, and then starvation is not possible in that case. Okay, Saurabh, I'll get back to you regarding this. I need to just think about a scenario where it will happen. Yeah, I'll get back to you. Okay. So, like I said, does anybody have any doubts in Peterson's law? Why it will work? Or why, or is there a scenario where it will not work? So one thing is that all the solutions we have seen so far is essentially only applicable to two threads. But in a sense, we'll have a lot more threads running. So yeah, we can extend this idea to n threads. So we'll see that. So yeah, as I said earlier, mutual exclusion is definitely guaranteed. Deadlock is not possible, and there is no starvation. But the solution can only be used for two threads. So can we create something for n threads? So such a implementation exists, and that is what we call as bakery algorithm. So it's a mutual exclusion algorithm which works for n threads. So we maintain something called as order of arrival using increasing numbers. So for every thread, depending on the order of arrival, we maintain something called as a label, which will essentially assign a specific number to this thread, and yeah, this will be always increasing. So this implementation, of course, there is I think in the while loop there is I think there's a small typo. It should have been there exists a k which is not equal to my id. So for all the other k values, which is all the other threads, we check if it is not my id, and that is when we execute this while loop. So what happens is that flag of my id essentially says the same thing as earlier, which is that it says I am interested in going into the critical section, which is that the current thread is interested in going into the critical section. And then in label, what we do is so label is essentially used to maintain an order of which thread came first, and that thread will be allowed to go into the critical section. So label of my id will essentially be one more than the maximum label that is present in that array. So label is essentially an array which contains n elements. And then what happens in the while loop is that we check if there exists a k which is not my id, and if for that k we check if that k is interested, and if that k is interested we check if that case label is less than my label, which is that which of these threads, did k come first or did my id come first? What will be the value of max label if it is not initialized for the first thread? We'll assume that it will be, let's say, okay, max label. Let's assume it's initialized to 0, all the elements in label. In that case, max label will essentially return 0. So label of that, yeah. So is the while loop clear? I think there's a typo in the while loop there. It should have been there exists a k not equal to my id. That's not actually an exact proper C syntax, C++ syntax. I just wrote it for convenience. We should actually run this in a for loop, which goes from 0 to n, and then for each of those k, we should be checking this while loop. So I just wrote it for convenience. So you can go through this while loop and see if you understand this whole locking situation. So essentially, as I was saying, so we check if there is any other thread which is interested in going into the critical section, and then we check if that thread's label is less than whatever label I have. In that case, if both of these conditions are true, then we don't proceed into the while loop. I mean, we get stuck into the while loop. And that construct of label of k comma k less than label of my id comma my id is essentially, first we'll check if label is the same. Label is less than the other label. But if both of them are same, then we check. Then we break the tie using this. We break the tie using the thread IDs itself. So if both of them arrived at the same time, at that instance, because this max is not an atomic max, so this max can return, say for two threads, thread 1 and 2 come at the same time, and the max of label can be some value. It can return the same value for both these threads. So it's possible that label of two threads might be the same. So if both of these labels are same, then we just take whichever thread which has a lower thread ID. So we are, of course, for threads which arrive at the same time, we are just assigning it. We are just giving priority to the one with lower thread ID. So just have a look at this and see if there is any doubts that you have with respect to bakery algorithm. Okay, so if there are no other doubts, then we'll move on to a conclusion statement. So locks are usually prohibited on GPUs because busy waiting is inefficient on GPUs. Like we want to exploit massive parallelism. That is when something is not doing any good work, we like any useful work. We want to schedule a different set of threads so that we can get super linear speed up or something like that. So we can, but it is possible to implement locks on GPUs, even though it is not recommended because it introduces a lot of serial behavior to the implementations that we have. So in order to implement locks on GPUs, we use atomics. So we'll see what atomics and how to implement locks with atomics. So atomics are primitive. Before that, anybody have any doubts? Saurabh, I'll get back to your doubt on this thing. Any other doubts? Anybody? Yeah. So we move on to atomics. So atomics are, we can say them as primitive operations, whose effects are fully or either it will be fully seen or it will be partially seen. Like when we saw that example of load, update, and store, uh, it was possible that the effects of this whole instruction, which was a plus equal to some value, was partially available to us. So it was we can see that a stored the value as 10 and another thread stored the value of a as 20. So we saw partial output, which is that we did not see the whole expected output. So atomic operations will not behave like that. It will either be fully visible or it will not be partially visible. It will never be partially visible to us. So atomics can only be implemented with the support of hardware, and it works with both the global and local memory. As with shared memory, I have to actually confirm if it works. I'm not sure, but I think it should be possible with shared memory as well. So let's take this small piece of code, which essentially increments the value of a specific variable. So we have two launches. So what are the possible outputs for the below piece of code for both these launches? So So just take a minute and see if you can come up with the possible outputs for both these launches. Let's assume the initial value is 0. So if you see 0, 1, 2, 3. Saurabh, how did you get value of 3? So wherein your answer is correct, it will be either for the first launch it will be 1, 2, and for the second launch we can expect. Actually, output case 2 would definitely be okay. Output case 2 is should the value would be 2 in the case of the second launch. For the first launch, it can be either 1 or 2, but for sorry, for the first launch, it will be either 1 or 2, but for the second launch, it will definitely be 2. So why is this the case? Yeah, so it is in a wavefront and we have 2 threads, so both of them will increment. So the output will be 2. So we'll have 2 increments um, by both the threads. Okay, if the increments are happening, but that is true. It will be the increments will happen at the same time, but both the increments will be visible. They'll be looking at the same instruction, but they'll do the increments twice. Okay. Sorry. Okay, that is, I think, yeah. That is, yeah, it is confusing. I think if it is, even if it is, yeah, if it is, then you're right. There are multiple possible scenarios, but yeah, 3 is possible. 0 is not possible in any case. I'd say 3 is possible. 4 is also possible if it is launched one after the other. Actually, in that case, it will be, that is correct. But anyway, I think definitely 2 updates will be there. So 1 is also not possible in that case. So it'll be 3 or 4 will definitely be possible. I think 2 is also possible, but 1 will not be possible because we have 2 kernel launches and at least one of them will definitely update it. In case 2, read, update, write are happening at the same time. Exactly in the same. That is correct. In case 1 goes. Okay, so when it comes to wavefronts, we can expect it to be a little different. So, sorry, there are multiple questions. 0 after both launches might be. Okay, so one thing is that like what I wanted to ask was that if the first launch happens, so this is not a sequential operation. Like it's not like both the kernels are launched. I think it is confusing from the slides. The thing is that 2 cases are there. One is that we launch using the first launch configuration, and in another case we launch with the second launch configuration. So it's not like one is happening after the other, but that is also an interesting thing to look at if both of them happen one after the other. Okay, so Viren is asking if in case both the threads write the value of 1 at the exact same time. So when it comes to atomics, that is true that both of them will be seeing the same instruction, but they'll make sure that the value that they read is consistent. So we don't need a specific synchronization constructs, or don't need the atomics as such when it comes to wavefronts. So okay, but anyway, I'll confirm regarding that. It's a good question, Viren, but I just need to confirm if there is any other specific case where it may not work. But as far as I remember, it is not required. So, okay, Prasanna is asking X of 0 after both launches might be 2 or 3. That is correct, Prasanna. Let me just have a look at 2 or 3. 3 is possible because 2 is also possible because at least one increment will be there. 2, 3, or 4, I guess. Will both actually 2 or 2? It should be actually 3 or 4, Prasanna, right? Will both the threads attempt to increment X of 0 at the same time? That is possible, except in the launch 2 case, those increments will be visible to, like, it'll be visible, like it will be like an atomic operation. But when it comes to the first launch, it will be not atomic. Prasanna, you.
Okay. Yeah. If they're incrementing at the same time, again, depending on the exact timing, I think it could be 1 or 2.
That is true. Like for the launch one.
I missed. Are they running concurrently? Sorry, I didn't understand if they are.
So the thing is that yeah, this is a little confusing, the question, I think. So what I wanted to say is that so suppose it's launched with this launch configuration 1, which is 2 blocks and 1 thread. What is the output? And then I wanted the output for the second launch configuration. So that is what I was trying to get it. But I think that the other question, which is that if both these kernels are launched one after the other, then that also is actually interesting question to look at. But yeah,
I think will it be some kind of race condition if they are running?
Race condition is definitely there in launch 1. As for launch 2, because they are in the same wavefront, if I'm not wrong, like Viren had pointed out, if because they are running in, they're looking at the same instruction and they're looking at the same data instance, is it possible that they may only increment once? So I need to actually check that, and I'll get back to you regarding that. But yeah.
Okay, I see Viren's comment now. Okay, thanks.
So right now the assumption is that within a wavefront, these operations will be atomic. But yes, I'll confirm that probably by the end of this lecture, or if not, I will confirm tomorrow. So how can we make sure that this behaves how we want? So we use a construct called as atomic increment. So we'll see more about these constructs in the next slides. So what atomic increment does is it makes sure that only one thread is doing load, store, and load, update, and store at a single time. So essentially, there will not be interleaving of load, update, and store between threads. So one thread will try to increment it. So and that thread will definitely increment it properly. So let's say thread 1 comes, it tries to increment, and it will increment, and then it will completely increment before thread 2 can start reading the value of the existing value. So yeah, again, we'll just so how do we update the SSSP problem? We instead of just assigning it, we'll do atomic min of the. So this is the only change. Earlier we just assigned list of neighbor as new distance, but here we'll do an atomic min, and just make sure that only one thread, only the current consistent value is read, and only that will be updated. The minimum among these values will be updated. So we'll see these functions in detail in the next slides. So the first atomic instruction set, and this is quite kind of an important atomic instruction, because using atomic gas we can implement any other atomic instruction, because this can be used to implement locks, and if we can implement locks, then obviously we can do any kind of other atomic instruction. But again, the functions or APIs given to us by HIP would be more efficient when it comes to atomic. So even if we have atomic gas, we try to implement atomic min or max using atomic gas, then that might be actually slower than what HIP already provides to us. So we'll see what atomic gas is. Atomic gas is essentially, it just means that it compares and swaps. So atomically. So the syntax is given here. So so what happens here is that atomic gas, it reads the value at address. So this will be a pointer variable, and it reads whatever value is there in that address variable, which can be in global or shared memory. So yeah, I think I was confused if shared memory could be used. So yeah, shared memory can be used. And then it computes this statement. So what it does is it compares that value against this variable called compare. So compare would be, let's say if you are dealing with integers, compare will be some value, and atomic gas will read the value stored at this address and then compare it to this variable called as compare. And if that is true, if the comparison is equal, if both of them are same, then we'll update the value in address with this third parameter, which is val. And then this whole function will return the old value, which is whatever was the original value stored in address, that will be returned. And yeah, so that is the whole idea behind atomic gas. So it does this atomically. So there's no when this happens, there is no other operation which can interleave this compare and swap operation. So there are multiple things happening, which is that first we are reading the old value, then we are doing a comparison operation, and then we are updating the new value, whether it's value or old. So all this happens atomically. So this atomic gas can be used to implement locks, and we'll see this soon. So does anybody have any doubts with respect to atomic gas? Or any other previous implementations?
So is it data type specific, or it's
yeah. So there are, I think, you can use integers, then unsigned integers, long int, and long. These four are the ones which are supported right now. At least in CUDA, these are the four variables which are supported. But I think in HIP also it should be the same as far as atomics goes. But yeah, I have to confirm if what we do of the depends. It will be helpful when we do logs. When we implement logs, we'll be using the value returned by atomic gas. So we'll see that, and I think it will be clear when we see how we use it. Yeah, as for Prasanna's doubt, yeah, these four are these four are what are supported. I believe 16-bit, 32-bit, and 64-bit words are what is supported by CUDA, and HIP should also be supporting it. But I couldn't find any documentation as to which exact data types will be supported. Yeah.
All right. Okay. Thanks.
I'll see if I can get it. But yeah, obviously we can't use characters or strings, double quotes. These are not supported. Yeah. Okay, then we have atomic min max, which as the name suggests, it finds the maximum value and returns the maximum of both the values. So if we have an address, So what happens is it reads the again this will be a pointer, address will be a pointer, and we read the value, which is the old value in the address, and then we check which is the maximum of old and then value. So old is the value stored at address, and we compare this val and this old, and whichever is the larger of them will be stored into the address, and the old value will be returned to us. So and there is a similar atomic min as well, along with an atomic max. And then we have atomic add and atomic subtract. So again, it's the same thing. So it reads the old value at address and then computes old minus the val, and then stores the result in the address variable itself. Again, it returns the old value here. So these are like some popular functions, and then we have these other atomic functions called as atomic increment, atomic decrement, atomic dic, then atomic and atomic or and atomic XOR. So we have all these different atomic functions. So yeah, and these are pretty much the same for multiplication and division. That is not there as far as I know. It's not there. Yeah. Yeah, atomic model is not there as far as I remember, but again, I may have to check that. But yeah, atomic increment, decrement, and HIP has some other specific unsafe atomic operations, but I'm not very sure what they are, but I saw them in the documentation. That is not there in CUDA as far as I know. It might be some version of atomic increment which may not be properly using logs or something, but I'll have to check what exactly that is. But that is something that you can keep in mind, that there are a few features in HIP which are not present in CUDA. So yeah, these are the different atomic functions which are available to us. I think there's one more called atomic exchange, which can be used to atomically exchange the value at two variables. So now we'll move on to any doubts so far with respect to what we've seen in atomics. Okay, so we move on to implementing how to implement logs with atomic gas. So you can take a moment and just come up with, if you have any ideas regarding how to implement a log mechanism on the excuse me. Sorry about that. Okay, so you can take a moment and then see how we can implement a lock using atomics for a critical section on the GPU. Like, if you have any ideas, you can post it. You don't have to write the code exactly. And then this will be a general lock for multiple threads. Okay, so is this a possible solution that we can have? This whole so our lock mechanism would be that we use atomic gas on a lock variable, and we assume that this is allocated at global memory, which means that we've used hip malloc to allocate this variable, and then we are using atomic gas to check if the current value is 0, and then we if it's 0, then we make it 1. So any thread which sees the value of lock variable as 0 will make it 1 and then proceed to the critical section. And when it exits the critical section, it will make the lock variable as 1. Checks if the lock variable is 1 and then makes it 0. So will this work as a lock? So the problem here is that there is no, mutual exclusion is not guaranteed, right? So what happens is that even if this atomic gas, multiple threads try to execute this thread, what happens is this statement, atomic gas, so first thread will check if its lock variable is 0 and then it will make it 1. So the second thread will come, it will try to do atomic gas and sees that the existing value is 1 because lock variable is 1. So it will not do anything. It will just exit this atomic gas and then go into the critical section anyway. So there is no mutual exclusion here whatsoever. So yeah, that is one problem, and this is not a solution. It is not a proper piece of lock. So yeah, there's no waiting at the intersection, and yeah, this can lead to multiple threads executing in the critical section. So if lock variable is equal to other ID, critical section else wait. Other ID. But we will be implementing this for multiple threads. It will not be just one or two threads. So if my ID critical section else wait. Just a minute, guys. Yeah. Extremely sorry about that. There was a small confusion here. So, okay, we're just saying if lock war equal to my ID critical section. Okay, yeah. So we'll see. So we've added an if statement. So only if this is true, then we go into the critical section, and if not, then we will not go into critical section. So can this work? Because of the lack of time, I'll just go ahead and say that okay, this will also not work because here what happens is if this atomic gas, if it returns a value 0, then that thread will proceed into the critical section. So for any other thread which does not, which is not able to properly set the value, compare and swap the value, they'll not execute the critical section. They'll just go and do the other instructions after that. So, but we want all the threads to execute the critical section. So, yeah. So that is the problem here. Threads which fail the condition will just continue to the instructions and will never execute the critical section. So finally, this is a almost possible correct answer, but there is something which can go wrong. So what happens here is that we have a do while loop, and this Saurabh, you had asked what we do with the returned value of atomic gas. So this is a place where we use the return value of atomic gas. So what we do is each thread will try and to compare and swap the value, and at least one of them will one of them will correct the to get properly compare and swap the value as one into log variable, and for all the other threads uh, the value will be 0. So the value will be 1 because only the thread which properly updates the value will get the old value 0. For all other threads, the value will be 1. And then it checks, then all the threads will check this condition. But only the thread which acquired, which was able to properly set the value of logvar as 0 will break out of this while loop, and then it will do its critical section. So there should be a comment here about critical section. I think I forgot that, but yeah. So again, if I explain once again, so multiple threads will come and try to execute this statement, but only one of them will be able to get the value of set the value of logvar as 1, and that thread will get the old value as 0, and then that thread obviously this condition will fail, and that thread will proceed to the critical section. Whereas for the other threads, they'll have the value as 1, old value is 1, and they'll keep on checking the value. So what could possibly go wrong here? Because this is a there is something that can go wrong. I think we already once had a doubt regarding this in the chat box. So what can go wrong here is that when we come to deadlock, no, but when we come to, in general, if we have across wavefronts, like across different wavefronts, this will properly work. But within a wavefront, this will have a problem because suppose we are talking about threads within the wavefront. So thread 0 and thread 1 is executing. In that case, what happens is that thread 0 will say thread 0 successfully compares and swaps the values log variable as 1. And so the old value inside old value for thread 0 will be 0, and for thread 1 it will be 1 because it was not able to properly swap. It will just get the old value. So when it comes to this while loop, thread 0 will break out of this while loop, whereas thread 1 will not be able to break out of this while loop. So essentially thread 0 will wait for its wavefront threads, its like sister brother, its sibling threads within the wavefront to come out of the while loop, but whereas they'll not be able to come out of while loop because of this while loop. So the one which acquired the lock, one which was successfully made the lock variable as 1, will come out of the while loop and it will wait here, say wait after the while loop. Whereas the other threads which could not successfully set the lock variable will wait inside the while loop. So for wavefronts, they should be executing in SIMD manner. So this will obviously cause a problem, and they'll just hang. The wavefront threads will hang. So nothing will happen. It just hangs, and yeah. So that's a behavior that you see, like when you won't get any error. It just waits. You don't know what is happening, so it just waits there. So yeah, like I said, they'll hang because they execute in a SIMD fashion. So to fix this, how can we fix this for threads within a wavefront? This piece of code. So in order to do that, we move the critical section inside the do while loop itself, and we use the idea of thread masking, so that threads which were unsuccessful in setting the variable, they'll just execute a no-op. So it's the same idea. We just added this if condition here. So we do old equal to atomic as. So one of them will successfully get the old value as 0, and the others will get it as 1. So, and only for the thread which successfully obtained this previous value as 0, they'll execute the critical section, and then they'll set the lock variable as 0. So Again, here the other threads which were not able to successfully set the value, they'll just execute a no op because this condition is not satisfied for them. So they'll just execute a no op while the one which satisfied goes into the critical section. And then once it's done with the critical section, it unlocks by setting the lock variable as 0. And then it continues in this loop. Again, there is no coming out of this loop. If you see this loop, this peculiar kind of a lock. But yeah, we can add specific logic to make sure that it works in all cases. But yeah, this properly works as far as locking, as far as mutual exclusion is concerned. This will properly work. Does anybody have any doubts? Okay, we'll move a little bit more quickly because yeah, we're running out of time. Okay, so we've reached barriers. We have, I think, 3 more topics. Hopefully, we'll be able to. I'll just see which all I can cover, and I need to cover a few topics in HIP as well. Some rather simple but quite important topics. I'll cover them tomorrow. But as far as synchronization, I'll just start with barriers, and okay, there is some problem with this. So barrier is essentially a program where all the threads need to reach before any other thread can proceed. So if you remember HIP device synchronize, that was a point where we needed all the GPU computation to be over before we proceeded to the next one. So that's an example of a barrier. And so the end of a kernel, like once the computation of a kernel is over, that acts as a implicit barrier for all GPU threads. So if you have multiple kernels executing, only once all the threads of like multiple kernels executing one after the other. In the queue, we have kernel 1, kernel 2, and kernel 3, and we have multiple threads for each of them. So kernel 1's only once all the threads of kernel 1 are complete, only then it will move to the second kernel. So that acts as an implicit barrier. And then within a work group, we use sync threads. Sorry about this. I think I missed escape character in LaTeX, so I'll fix this before I upload this. And within a work group, we use sync threads to synchronize all the threads within the work group. So how do we synchronize threads within a wavefront? So the answer is that threads within a wavefront. Yeah, that is correct. Overin, you're right. So threads within a wavefront will also always be in sync. How about across all the work groups? So we use something called as a global barrier. Global barrier acts as a barrier across all threads on the GPU. So earlier what we did is that we had to use the idea of implicit barrier provided by a kernel in order to do a global barrier. That is that like if at a specific point in our computation we needed all the threads to be to wait, then in that case we would break the kernel into 2 parts, and so one kernel will be till that point, and once that kernel is over, we launch another kernel with the second part of the original kernel. So that is what we had to do earlier. But then they came up with a new idea of grid.sync, which essentially adds a global barrier. So we don't have to do the whole splitting of the kernel into 2 parts. So this is how you add a global barrier. Essentially, you have to use this header file, and then we use the namespace cooperative groups. And within the kernel, you call this function within that namespace, and then you can just call grid.sync. So all the threads will come and wait here till a split of a kernel in terms of like if say my kernel had 4 lines, and after 2 lines, after line 2, I needed all the threads to come and wait there. So what would happen is that I'd make one kernel with line 1 and 2, and then another kernel with lines 3 and 4, and then launch them one after the other. Okay, I think the syntax is a little misleading. That's not exactly what it means, but this is how we do it. I'm not sure why they named it. Even I had the same doubt when I heard this for the first time. It was like, why are we calling it grid.sync? But we are actually synchronizing all the threads across all the grids. So maybe we can see if this it's syncing all the grids or all the work groups. We can think of it like that. But yeah, this name can be a little misleading. So that is global barriers. So yeah, we can implement a global barrier of our own in case for earlier versions of HIP or earlier versions of CUDA, this grid.sync was not available. So we can implement such a global barrier which works across all the threads that can be implemented on our own. So we'll see how to do it. Okay, I was actually planning to give this as a classwork, but since we're out of time, I'll just show you how it's done. So yeah, we have two global variables. So this, I think, this is not something that we've seen so far. So this essentially means that there are two cases when we use this. We actually prefix this to a variable declaration. This means that, and this will be put on the host code, not inside the kernel. So this means that this is a global variable on the device. And when we prefix it to a function, it means that it's essentially a device function. So we don't always want to, sometimes we need to, extract out certain big pieces of repeating code into a function. And if we only use that function inside the kernel or inside the device code, then we can prefix it with device. So this I'll cover tomorrow in the special topics, provided I get enough time. So this is essentially an implementation of the can global functional device access other global functions, other global functions or global variables. Okay, I did not get your question, Viren. Global functions. Okay, so when you say global functions, these are just function definitions which are okay. These are not kernel methods essentially. These are just device methods. So this function can only be called from either another device in another device function or from within the kernel. But yeah, different kernels can call the same function. That is possible. Yeah. So essentially, what this does is it just checks if thread id x.x is equal to 0. So what? So we take the thread 0 of each block as the representative of that block, and then we check if that is the thread that we need, and then we maintain a counter. Okay, here also I think we missed something. We maintain a counter which just counts how many blocks we've seen so far. So the synchronization method will take the total number of blocks that we have launched. So we for each of these blocks, we increment the counter value. We use atomics, and the counter value will at the end contain the total number of blocks. And then we check if we've seen all the blocks. If the counter value hits num blocks minus 1, which means that we are seeing the last block which is come into this if block. If that is the case, then we reset the value of global counter to 0, and then we this is atomic exchange. Then we exchange the value of then we make the value of global flag as not like it will make it 1, and then it will proceed. So because it's initially 0, it will make it 1 and store it here, and then after this we have a sync thread. So this means that all the threads within the block will come and then wait here till thread 0 completes its execution, and then after that we just check if the global flag is not 1, then we just busy wait here. So once the last block comes here, it will make the existing value of global flag as 0. At that point, all the blocks will break this loop and then come out. And after this also, we'll just wait for all the threads within that block to hit that point. And then after that, we'll just, so this will essentially synchronize all the threads within that block, within all the blocks. So I know I kind of rushed through it. So if anybody has any doubts regarding this, I think we take it tomorrow because I think we're already out of time. So we'll close here for today. And if anybody has any doubts, tomorrow morning in the morning session. So I'll be here from 9:15. So if anybody has any doubts and if you want to clear it out, and if you can come early, you can come a little early, and we can discuss more on this. So I'll stop here today, and we'll continue with global barriers tomorrow. And yeah, I'll answer the doubts, and hopefully we'll be able to finish synchronization tomorrow, and then touch on a few topics which are kind of interesting or kind of important. Okay, we'll close here for today, and yeah, thank you for joining. We'll meet tomorrow. Sir, yesterday's recordings are not available on the sheet. The main session will start at 9:30 to, it'll be the same time, 9:30 to 11:30. But yeah, I'll be coming a little early in case if you guys have any doubts. Yeah. And Saurabh, yesterday's recordings are available. Okay, the recordings are actually uploaded by Professor Rupesh. I'll just check with him. If it's available, and I'll ask him to upload it. It should be available, yeah. I'll speak to him today. Pranod is asking if you will implement all that was discussed. Why I skipped the whole showing the code part is because there's not much output that we can see when it comes to synchronization. There is one code that I had written where that is coming up, which is the printf. If we remember, we printed the for loop we parallelized the for loop and we printed all the numbers from 1 to 1000. Actually, the square of numbers from 1 to 1000, and we wanted to see if we can put it in a sequence. That code I had written, but that's in the coming slides. But as for the others, like there's not much output that we can see here. Like, even if there is deadlock, it may not be possible to see the deadlock in action. Or yeah, like there are questions which have different outputs, right? It's not always possible to see all the different outputs. So that's why I thought, okay, something which has output, I'll anyway. Yeah, the code, okay, it's not uploaded on Git. But I've shared it in the Excel sheet along with the video recordings. There is a folder called code examples. In that, I've put the examples that we've seen so far.